screen is visible to you?
Yes, sir, it is visible.
Okay, so you can see there are
Yes, sir.
two codes. So all of you just hold on, just see what I'm doing first. So just open two windows like this, and first window is called as pole to time domain response. So this is the name of the code I am given. So in your WhatsApp I have sent two codes. First code is pole to time domain response, and second is inverse Laplace. So you open, it's a very simple one line code. So just open two windows and just come here. So just see what is the step I'm doing. Students, are you with me? So just see what I'm doing first. So a lot of work will be left to you. Just see what I'm doing, the way I'm doing it. Okay. So here, uh, should I start? Should I start? Even if you have not got it, don't worry. Okay, even if you have not opened the MATLAB or something, don't worry. It's a very one line code. It's a very simple code. It's a one line code, not big. Okay, so this is the first code of inverse Laplace. So name is inverse Laplace. The way I have written, you can open. So don't say inverse Laplace. It will not. It might not get. Okay. So what is the function? Function is I Laplace. Are you with me? I find 40 students. Okay. So I Laplace. So this is something. So the things that you have to find is Sims. What is meant by Sims? SYMS. Sims actually is the short form of systems. So if you please have pen and paper, Abhishek Kolhapur. Okay, so those, if you're having pen and paper, please, I'm admitting it is not getting admitted. Okay, so if you're having pen and paper, please write down. So first thing you find out what is meant by Sims, SYMS. So this is the second code that I have sent to you. Okay, first code is this one, plot to time domain response, and second code I have sent in your WhatsApp is this one, that is inverse Laplace. So there two functions are there. So CLC, close all, clear all those things are there. There are two functions. One is called as I Laplace, another is called as Sims. Is it understandable? Just say yes or no. Don't write anything in the thing. If you're having doubt, please ask for my time, because I cannot see my Google Meet link. Is it understandable? Just say yes or no. So Sims and I Laplace, these are the two functions you have to check. Okay. And here what I'm doing is f is equal to 1 by s square into s plus 2. Hello. Okay. So what is now closed loop transfer function? So this f I will call as, maybe this f I might call as CLTF. Okay. So I might call it that, CLTF. And I Laplace of, you can say CLTF. This I can do. Okay. So now save. So to save, you have to go to editor and save it and then run. And you are finding what is the inverse Laplace. So this much small is the work that we have to do. So what is that inverse Laplace we are finding? It is t by 2 plus exponential of minus 2t divided by 4 and minus 1 by 4. This much you have to do. So you have to represent what is the closed loop transfer function here, and after that, so that is actually Sims S. So Sims S means we are defining our transfer function in S domain, and every S is small. So whatever is the closed loop transfer function, what was our actual transfer function? Just now we have done. So for actual thing we have done CLTS is equal to 1 by S plus 5. That is what we are supposed to do. Okay. So let us first do the known system. So this CLTF I will take as percentage. So this is actually the code. This is actually the code, only 2-line code. It is not a big thing. Okay, so save it and then run. I'm sorry, there is a problem. That is, I have used two brackets here. That's why it is giving error. So dot. दिख रहा है नीचे? Exponential minus 5t. That means what is the time domain? Response e raised to minus 5t. Actually what we are plotting here is the impulse response. Okay, actually what we are plotting here is impulse response. Now e raised to minus 5t. Students, are you with me? Anybody having any doubt? Anybody having any doubt, please type here. What we are actually finding is we are trying to find out impulse response by using MATLAB. That's a one line code. First line is sims s, okay, and second line is you are defining the CLTF, that is impulse response, or TS or YS you are defining, and then you are taking the inverse Laplace of CLTF or YS, and you are finding what is called as impulse response. Is it okay? Can I proceed?
Yes.
Okay. So you are not finding it very difficult or something. So 1 by S5 I have done. How can I find step response? How can I find step response? So I told you that whatever is the transfer function CLTF, or you can name it as TS also, or you can name it as YS also. Okay. So you can name it as YS. So Y capital, S small. So both you can say as small, doesn't matter. Okay. So you can say this is YS. So if you are happy with this understanding, let it be like that. Okay. So this is actually, so now it is easy for us. And YS, just put a semicolon here and solve it. So what actually we are plotting is actually YS. Okay. And actually we are plotting YT. So you can say I Laplace. So YT is equal to this. So YS is given, and now we are plotting what is YT. So now this might be your code. So you are finding impulse response, or you can say that impulse response. IMPULACRESPONAC. Impulse response is equal to I Laplace, that is inverse Laplace of YS. Okay, now impulse response is equal to e raised to minus 5t. Now you want to check how e raised to minus 5t look, because depending on that you can comment on stability. So copy this, whatever you are getting here, copy this. Okay, and go to the other code. Go to the other code. And what is the other code? Other code is this big one. This is again the same thing. CLC clear all, close all, and here you just press whatever you have got. So this is percentage. Okay. So what I'm doing is uh, X. So this is my code now, or you can say here impulse response like this, and here you can copy. So now you just save it. Below I think there is nothing. So a lot of codes are written for different waveforms, and now it will plot. So up to 20 seconds we are plotting, and 20 seconds we are plotting with respect to a time of 0.01. That means 20 by 0.01. That means almost 2000 points we are plotting. Okay, so this is how it will look like. So it does not look like this. So this is TTT, it is there, not necessary. Okay, so let us not look at this waveform. Let us plot t comma impulse response, and let us see what we get. Okay, now see what we are getting is very fast it is falling. Okay, like this we are finding that is starting at 1 and it is coming to 0, like this. So if you want to enhance, you can enhance it. So there are a lot of commands like this access. So access like this. So whatever is the access command you can put here. So this is here like this. Now you can specify the time. So it is almost falling to 0 within 1 minute. So 1 second. So what I'll do is x min is 0, then y min is almost 1. Okay, x max, y min is again 0, and y max is 1. So the same graph, I have put a access command and then I will run like this. So I'm actually zooming it. So first I've plotted what is the response, and then I'm checking. I'm just putting it zoom. So you have plotted the response, but this thing is not taken. So this is x min, x max, y min 1, y max. Here in line 9. Okay, so access, why it is. So 0101, if we do, it is not responding actually. Let us find out what we are getting. Okay. Is it understood? So what I have restricted is I have restricted it to 0 to 1. So you can find here from 0 to 1 it has plotted. So this very sharp curve you can find out like this. Okay. So now again go back to inverse Laplace. Now again go back to inverse Laplace and let us find out what is the step response. So ys is equal to, so impulse response we have done. So I will just change this to step. Yeah, any doubt? Who is this? Okay, so I will now just plot the step response, that is 1 by s into s plus 5. So step response we had found as 1 by s into s plus 5. I'll remove my video. There is a bandwidth issue. So like this. Now I will say that I will plot for step response. Okay. So I'm just showing you this one example. Now I can give you any impulse response and you can find any step response. So step response, so 1 by s plus 5 was the impulse response. Whenever you are trying to find out its step response, you have to just divide the whole transfer function or ys by s. So this is what I have done. Now save it and run. And just check what is the inverse Laplace you get. So I have got the same thing. I have shown you this proof, that is 1 by 5 minus 1 by 5 into e raised to minus 5t. Now what you have to do is you have to copy this. You have to copy this. So there are two codes which are running simultaneously, and instead of impulse response, you just put another thing, step response is equal to, and copy this. So instead of impulse response, you make it step response. Okay. And this thing axis, don't put it now because we don't know what is the response now. Okay. So this impulse response also you can. Okay. So this is the code now. This is the code now. So I'll be leaving many of the job to you now because you have done this MATLAB on ramp and everything. So I'll just mention the impulse response, and I'll ask you to do all the impulse response and step response in time domain. So this is what is done. So close all, clear all, t is equal to 0 up to 20, vt greater than 0. Okay, so we are saying that vt greater than 0 means we are plotting everything in the causal domain that is greater than time. Now step response, this equation you have to get from the previous code. Okay, so just this equation 1 by 5 minus e raised to minus 5t divided by 5. This we are getting from the previous code, and after you get this, plot step response. So this is your main code, and this line, this equation you have to got. How can you get it? This line, go to the inverse Laplace, and there ys equal to 1 by whatever is the transfer function given, there you divide by s. So I will be giving you almost 15 to 20 different transfer functions in impulse response, and you have to tell me what is the impulse response as well as step response. So I'll give you impulse response maybe around 20. So first you have to take the inverse Laplace of that and you have to plot it. So for plotting, the other code is there. So this code is there for plotting, and the first code is there just to find what is the inverse Laplace. Okay. So this is the combination of this experiment. So now I have shown you two cases like this, like this. So inverse Laplace 1 by s into s plus 5. Now I give you another case. So both impulse response and step response you can keep here, and I give you another case like step or impulse response is equal to. I'll give you another case that I will give you two real-time poles. So we have to have an extra session somewhere, and there we will see all these cases. Suppose s plus 3 into s plus 5. Okay. So these are two pole system. This is a second order system. Now what I am going to get. So this step response thing you now hide it. Now I give you two cases, that is ys equal to 1 by s plus 3 into s plus 5. This is what I am doing. So this is 1 by s plus 3 into s plus 5. This is what I am doing. Okay, and impulse response is equal to I Laplace of ys. So I made the change in the wrong place. I'm sorry for that. Here I have to make the change. So more complex system, more and more complex system you have to take. So same as means you are defining the system in Laplace domain. Now ys is the output. Now I am giving you the impulse response 1 by s plus 3 into s plus 5. So these are two pole system where there are two real poles on a real negative side of j omega axis. So there's the impulse response given. First find what is the impulse response. So and then we will find what is the step response. So for step response we'll divide this ys by another s, and we'll see. Now see, okay, this is the impulse response we have found. So that means if I give you ys, this is how to find the inverse Laplace transform. Now you have to copy this, and take it into the other this thing. Okay. And here you just write down that impulse response, is equal to this. Okay, like this. And plot step response, you can do this, or you can write as like this. So whenever you are finding impulse response, at that time this thing should be commented. comment it like this. This is the first case. Now you plot it. So here instead of step, just write impulse. This is what it is. And now save it and run it. So this is a process more than the numerical. I am telling you the process. So now previous case I gave you only one system, 1 by s plus 5. That was a one real pole system. We found out impulse response. Then ys we divided by s. Then whatever we got at step response. Here I have given you a two pole system. So now I will keep on increasing the complexity. So it's s square plus 8s plus 15. That is the transfer function now. If you multiply s plus 3 and s plus 5, you'll be getting s square plus 8s plus 15. And first find what is the impulse response. So take the inverse Laplace, you are getting this. Take this equation e raised to minus 3t by 2 and all into this. Now for whatever time given, you can make it 10 and you can make it 0.1. Okay, just for fastness in the calculation, plot it. So we have found what is the response of the system if there is only one reducing exponential. Now we are finding if there are two reducing exponential. Just check. Okay, so if there are two poles and both are on the negative real axis, so we'll be having a session maybe tomorrow around afternoon from 5 onwards or maybe 6 onwards. There I will show you the pole position and what is the response. So if you want axis, you can put an axis command here just to check. Okay, so you're finding it like this. So you can take this axis command and you can bring it here like this. You can bring it here and axis. So after you have seen what is the response, now you can plot from 0 to 3. Okay, 0 to 3 means because here almost it is up to 3, it is coming to the ground, and height is 0.1. So just check that amplitude has reduced now. So you can do it as 0.1 like this. So after you see the initial response, now you can expand it. So this is kind of a zoom that you are doing. And if you want it to be very smooth, like, so make it 0.1. Okay, so these are the changes that I have made and now run. So previously it was up to 20, now it is plotting up to 0 to 3, and amplitude is 0 to 0.1. Now see, this has become smooth, very smooth, because I have increased the number of samples. Okay, so this is what if there are two negative real poles, then this is the time domain, or this is the impulse response. This is the impulse response if it is time domain like this. Okay. This step response was pending. This step response was pending. So let us plot this step response first. So this step response I had shown you. So comment this and uncomment this. So this step response was actually for the previous system. Let us find out. So uncomment first. One more plot we'll do and we'll stop. So this is the step response for the first system, that is 1 by s plus 5. 1 by s plus 5 was the impulse response, and then we divided that by s, because s is the first step, and it will be an increasing kind of a response you will find. Just check. Okay, so this is the step response for 1 by 5 minus e raised to minus 5t by 5. So whatever impulse response you had seen, e raised to minus 5t, this is the step response for the same system. Okay, so 1 by s plus 5 was the impulse response, and step response was 1 by s into s plus 5. So you had done the partial fraction, and after that you converted this thing into time domain. You found out 1 by 5 minus e raised to minus 5t by 5, and this is the response for that. So you can give an axis thing here, and you can increase the time little bit. So you can just check the axis thing you can give here. Okay, axis thing, I'll just show you how to use the axis command. Anybody asking anything? Someone wants to join. Okay, join. So how can you change the axis? So first check what is the amplitude. So amplitude is up to 0.2. So you can keep this amplitude as 0.25. This is the first change, and you can plot it up to 0 to 4 likewise. So you just want to zoom this part. You just want to zoom this part. So there is tool here for zooming, or you can do the axis with a proper axis command. So this is the same graph, but I'm zooming the initial part. What is the axis command? What I'm doing? Okay, this is what is so this is the rising, fast rising, likewise. The last thing we will do is will find the step response for this system. Okay, so this thing you remove. So whatever is the system, 1 by s plus 3 s plus 5, this is a two root system. Now how can I find step response? So for step response you have to divide the whole transfer function, that is impulse response, by s. That means there is another s coming at the denominator. So if you're doing that, this becomes step response. So you have to do this ys and this becomes the step response. Only this much you have to do. Okay. So there's actually CLTF was given, closed loop transfer function was given 1 by s plus 3 s plus 5. I'm trying to find out step response. So whatever is the closed loop transfer function is given, divide by s. That is the first job. So I've done that and then save. So I'll leave you in 2 minutes. Please give me this 2 minutes. So now take the inverse Laplace and you'll be finding there are three terms now. So there are three terms. So there is a constant term which has come here. Just check. Okay. So there is a constant term here. So you copy this. So previously we had found out, so if we go there, this equation was the time domain response for the impulse response. Now if it is step response, so there you are dividing it with s, so a new term has been added. Okay, like this. So just don't show the axis command first, hide this axis command first, and just follow the step response. So for many input cases you have to do it. Okay, so all these things, time and other things, I am keeping as simple. So first I have given 1 by s plus 3 s plus 5. I took the inverse Laplace, I plotted the impulse response. Then how to plot step response? Just divide the whole thing by s, or just multiply s in the denominator. That's all. So this will be giving you a step response. So first find I Laplace of the step response. Then you are finding this equation. So from 2 now it has come to be 3 variables. Take this inverse Laplace transform and plot it in the time domain. So step response is the name of the variable. Now I plotted it and now plot it. Okay, and after plotting we can do some axis. Okay, or we can do some zooming. So let us see the same system which was showing some increasing type of input output response, how it is looking in second order system. So see, this is the step response of the second order system. So what we are finding is first order system step response and second order system step response, both are looking more like step. Okay, likewise. So this is the second order system step response, likewise. Now you can take a third order system again. So if I add another pole, okay, then what will it be? So here I can add another 0. So first remove this. So again this becomes a second order system. I add a 0 here. So I add a 0 here. Okay, let us do a unstable system. Let us do an unstable system and let us stop. Okay, so 1 by s minus 3 I will do now. 1 by s minus 3. So this is the last thing we'll do now. 1 by s minus 3, and let us find out impulse response only. Let's find out impulse response. So 1 by s minus 3. S minus 3 means this is a unstable pole which is in the right side. Let us first find out. So this is a two poles I'm giving. One is stable. 1 by s plus 5 is a stable pole, and s minus 5 is an unstable pole. And now you are finding what is the impulse response. So go to the impulse response thing and copy it here. Control V. Now impulse response, uncomment it and uncomment it. Okay, likewise. And here you comment. So you are finding here it is e raised to 3t divided by 8. So this is actually the problem. This is the culprit. So now you have kept one stable pole, one unstable pole. You are finding s minus 3 is the unstable pole because this is s plus 3. That means this is coming to the right hand side of s plane. So there is a impulse response given, and s plus 5. So there is minus 5. There is in the left hand side. So it's a combination of stable and unstable pole. So this is s minus 3 is the unstable pole. S plus 5 is the stable pole. So for that, whatever response you are finding, e raised to 3t by 8. So there is a increasing exponential and there is a decreasing exponential. Right? But you will be finding net effect is increasing only, because as time is going by, increasing effect will keep on piling up and decreasing effect will be keep on reducing, and huge amplitude you will find as time going by. We have only plotted up to 10. Amplitude will go in thousands and lakhs, you will find. Just check. Just check how it grows. So amplitude is 14 into 10 raised to 11. Just imagine how it grows. Okay. So this effect of the reducing effect of e raised to minus 5t, as time is going by, this is reducing, and as time is going by, e raised to 3t is increasing. So net effect will be increasing. So this is a unstable system. Okay. Likewise, and the same thing you can do in case of a step also. So how to find step response? Just multiply the s here. Just multiply a s here, and take a percentage and come to the step response. So the same thing, there is one stable pole, one unstable pole. I want to find out what is its step response, and let us see. So first you will get the inverse Laplace. So in inverse Laplace also you are finding there is e raised to 3t. So copy it in here, copy it in here. So in the step response you can copy it. Control V. If you want, you can leave the meet because you are having other lectures. So I'm almost done. I'm recording it actually, so I'll upload it. You can check the last part, 5 minutes. Okay, so those who want, they can leave the meet, no problem. So whatever step response I had got from the previous case, so 1 by s minus 3, 1 by s plus 5, that was the impulse response. I have just divided that by s. That means I am trying to find out the system response with step input as the input. I have divided by s, and then I have taken the inverse Laplace. So this equation I have found minus 1 by 15. So that I have taken in the plotting. So this is just a plot code, very small plot code that I'm doing. So step response, whatever I found from here, that I have put here. Now I'm plotting t comma step response, and save like this. So for a second order unstable system, we are plotting the step response, and you can check that the step response does not at all go close to the unit step. Okay, so even if you are giving a unit step input, so that's a kind of a bounded input, but what response you are getting is unbounded because the system itself is unbounded. Okay, so only for this part, only for this small part of e raised to 3t by 24, the whole response is becoming unstable. So this is unstable response because as time is increasing, so just see at 10 amplitude is 5 into in the range of 5 into 10 raised to 11. So huge amount of exponential increment is happening because there is a e raised to 3t part in the system. So likewise, I will now give you a lot of different cases. So real pole, imaginary pole, and all those things I'll give you. And first you have to take the inverse Laplace. You have to find out the inverse Laplace, that is yt for impulse input, yt for step input, and you can find out how is the uh, graph for impulse response and step response. So many cases will be asked to you, 10-20 cases. You just write down the case and plot the graph, and that will be it. So I have not written any theory for this, but whatever theory I have written now, this I can convert and I can give it to you. So small, maybe 1-2 pages theory will be there, and mainly this 10-15 graphs will be there. Together you have to submit it. So by next Monday, by next Tuesday, you can submit this experiment number 4, and experiment number 3, all the write-ups and everything was given. Please design the front page exactly the way it is given. Don't do it at your will. Okay, so whatever is given, exactly do it in the same way. So the code is now given to you. I will upload this whole thing by today evening to you. That's all from me now. Okay, so thank you for joining.